thanks for the nice introduction. Thanks so much for organizing this great symposium. I'm very grateful to have the opportunity to today try to give you a dynamical systems perspective on generative modeling, essentially. And I will basically try to connect these problems to different branches of mathematics, namely dynamical systems, but also optimal control, path space measures, and PDEs. I guess you all know that these methods or perspectives are highly connected, but I think some connections are maybe not so standard. And in particular, we will try to use these perspectives to eventually design new numerical algorithms to be able to sample and improve generative modeling. Before going into the details, I should mention that this work has been jointly done with Julius Berner and Jingtong Sun from Caltech and Nick Nusken from King's College. So to set the stage, I think I don't have to explain much here again because we had 2 talks on this already. The task in generative modeling is to sample from a complex, potentially multimodal distribution D. And I would say one can distinguish in 2 settings. Either the distribution could be defined by a bunch of samples. So I could, for instance, have these images here, which are my samples that somehow define my distribution. Or I could have given an unnormalized density, which is probably more prominent in the sciences. And I guess you all know that the first setting has led to really impressive results, impressive in particular because these problems are very high dimensional. However, the second case is, I would say, a little bit less mature, and this is why we focus on that case. So we don't assume any data samples, but only an unnormalized density. And to formalize this a bit, so the goal is to sample from this target density, which I write here as an unnormalized function rho and the normalization constant z. And the key idea is basically to start the sampling with an easy prior distribution, for instance, a Gaussian, and then let some evolution, some dynamical system basically evolve until a terminal time. And I want that at terminal time, my process is distributed according to the prescribed target density. And there could be 2 settings here. Either I could have an SDE as the one that I drew here, basically having this drift function mu and diffusion matrix sigma, or I could set sigma to 0 and consider an ODE, so a deterministic evolution. And the key idea in generative modeling is that I want to somehow learn this drift mu such that at terminal time the process is distributed according to the target, right? And so I want to kind of present you 2 attempts with which you can try to solve this problem. And I think the first attempt is not so standard, but I start with this anyway. It's basically starting with a PDE perspective. So I guess you all know that the density of this process is described by a partial differential equation. Namely, for the stochastic evolution, I have this Fokker-Planck equation here. And for the deterministic case, I basically by setting the sigma to 0, I get what people call the continuity equation, right? So these 2 PDEs describe my density evolution. And importantly, of course, I need these boundary conditions of the prior and the target at the terminal or initial time. And now the key idea is to basically try to identify pairs, Y and P, that fulfill either of the above PDE, right? And so we will try to then solve this, which will lead to different numerical algorithms. And the way we do it is we consider variational formulations of these PDEs. So we define loss functionals, which basically take two functions as an input and give me a non-negative number. And the loss functionals shall be defined in such a way that they are 0 if and only if a pair fulfills the corresponding PDE, right? And I should also mention for numerical stability, we usually don't operate on the PDEs that I showed before, but we look at the log transformed PDEs by basically defining this function v here as the log density, which then gives me these 2 PDEs, which I give a name here. I call it R for residual, because I will use this later. And this is what I get for the SDE case, and this what I get for the ODE case. If you look at the SDE case carefully, maybe you realize that this is actually, if you consider it as a PDE in V, nothing but a Hamilton-Jacobi-Bellman PDE, which is already hinting at a nice connection to optimal control theory, which I will comment on in a minute. Okay, so yeah, the task is basically to learn U and P simultaneously, and I guess as you probably already have guessed, this typically does not have a unique solution, right? Which is kind of intuitively clear because if I want to transport the prior to the target, I can have infinitely many dynamical systems that can do that, or like infinitely many bridges if you want. However, there are a couple of ways to make this unique, and I will mention 3 of them. One is typically called annealing. So here the idea is to simply fix a density path. So basically I fix Px, of course, such that I obey my boundary conditions, and then I only learn the drift here, right? So I define these new residuals here where I fix the V. So basically with this notation, I mean, if there's no tilde, then that's the solution of the PDE, and if there's a tilde, that's yeah, somehow an approximation which I still have to learn, right? So yeah, this is one idea, to basically fix the density path and only learn the drift. Another idea we just heard in the previous talk is a score-based generative modeling, which I will also comment on in a minute again, but for now, just believe me, if I fix my mu like this with an f suitably chosen, for instance, f could be minus x, as we saw before, then basically my loss reduces to a loss where I only have to learn v, because I have basically prescribed my density mu, right? So this also gives me unique solutions. Or I can consider the famous optimal transport or Schrödinger bridge setting, where additionally I try to minimize some regularizer on the drift mu, and then yeah, turns out that, I mean, then I want to find the mu, which is the gradient to a potential, and turns out that this potential solves also another Hamilton-Jacobi-Bellman PDE, which I wrote down here either for the stochastic case or for the deterministic case, right? Okay, so now I want to consider the attempt 2, which is probably more familiar to you, and considers time reversals and path space measures. So again, I draw this picture here, and yeah, this now only works for stochastic evolutions actually. But the key idea is that I have a forward process. So I denote here the forward drift with mu f. And I now introduce a backward, or I prefer to say a time-reversed process, which I call y, which starts in the target and runs backward in time, which I denote here with this backward boundary motion, right? And so now the key idea here is that I want to learn the drifts mu f and mu b for forward and backward, such that x is the time reversal of y. Because if I have done this, I have solved my task basically by definition, because I know that x capital T is then distributed according to the target. Here I have also a couple of choices. So either I can learn these 2 drift functions or controls, if you want, simultaneously, which yields a loss that we called L bridge. I can fix an annealing, which corresponds to a loss that was introduced a couple of months ago called CMCD. Or I can yeah, fix basically the backward drift suitably, which again corresponds to score-based generative modeling, where basically the backward process is not learned but fixed in a clever way. Okay. So now the question is, how do we solve this? And of course, I mean, we've already seen how we solve this, but we want to consider here the density case, right? So we don't have data samples. We want to sample from this unnormalized density. And here the key idea is that we want to consider path space measures. So with this, I basically denote measures on the space of continuous trajectories. And as you can guess, this Px mu f denotes the path space measure of the forward process, and this one here of the backward process. And now the very simple idea is that, well, if I want these 2 measures to agree, because, yeah, note there's this time reversal here, right? So if I want the time reversal to hold, I basically want these 2 measures to agree. So I simply minimize a divergence between these 2 path space measures in the drifts mu f and mu b. Because if I can drive this divergence to 0, then I know that I have solved my problem, right? So now the question is, how can I make sense of this numerically, of this kind of abstract viewpoint? And the key observation is that we can make use of this numerically, because if you then choose a concrete divergence, think of the KL divergence, usually you need somehow like log likelihood ratios of path-based measures or Radon-Nikodym derivatives. And it turns out that one can compute this Radon-Nikodym derivative between these two measures very explicitly. So this can be really implemented on the computer. You don't have to understand the formula, but note there's a deterministic integral, a stochastic integral, and of course the boundary conditions. Okay, so now we want to make it a little bit more concrete, want to discuss connections and equivalences between these two attempts that I discussed. We need to make a choice for the loss for attempt 1 or the divergence for attempt 2, right? And so let's take the first choice, and let's take a BSDE-based loss. So BSDE stands for backward stochastic differential equation. We have kind of the inventor of this loss in the room here. So just in one slide, I want to show you what is meant with BSDE loss. So the key idea of backward stochastic differential equations is that you get a stochastic representation of a PDE via Ito's formula, right? So take a stochastic process, it's defined like this, and a PDE that's defined like this, and that has here the infinitesimal generator and some nonlinearity. So that's the cool thing. It can consider nonlinear PDEs of that form. Then basically what I wrote down here is simply Ito formula. And now I can replace basically this thing here with the H from above, and I get this, right? And now the cool thing about this is that no second order derivatives appear anymore. So basically I traded my second order derivatives with the Brownian motion term here, which might be nice from a computational point of view. And now I can simply say I define a BSDE loss that minimizes this residual here, because if it's 0, then I know that Ito formula is fulfilled, and if it's fulfilled, then I know that my PDE is fulfilled. I mean, I'm kind of ignoring technical assumptions here, but yeah, in very mild assumptions, this holds. And of course, this expectation is with respect to the process X. Okay. So this I can do, and it turns out, so if you start with the PDE perspective and take this BSDE-based loss, then this is exactly equivalent to a particular divergence of in this path space measure perspective, namely this divergence here. I don't even know how this is called, but it's certainly a divergence. And we found this quite nice because you can really basically rederive what people have done before, and I make it a little bit more formal. So the BSDE versions of our losses for these log Fokker-Planck PDE I showed you at the beginning basically are equivalent in the sense that if I assume this reparametrization here, which for the experts is, by the way, Nelson's identity, then I realize that this log Fokker-Planck BSDE loss is exactly equal to the bridge loss. If I look at the annealed BSDE log Fokker-Planck version, then this is exactly equal to this CMCD loss that I mentioned before. And if I consider this reparametrization here, which is basically telling me that I want to have the score here, so recall that V is the log density, and then I recover that my basically BSDE PDE loss gives me back the score loss, which we called DIS before, right? So that's quite nice. Another nice connection, if you take actually the Kullback-Leibler divergence, then which I wrote down here, then this exactly gives us a stochastic optimal control problem, and I wrote it down here in a slightly different notation just to kind of realize the connection to stochastic optimal control better. So I just set the forward drift to be f plus sigma u. So f is a fixed drift, so think of minus x for the Ornstein-Uhlenbeck process. U is the control I want to optimize, so I have this SDE here. And I also fixed the backward process to have the score-based generative modeling setting. And now I simply define my loss basically to be the KL between this PXU, I call it now, and PY time reversed. There's a small detail here that I also make some approximation error because I can't let it run for infinite time, but you can ignore this, so just look at this. Then this loss can be written exactly as a stochastic, as a cost functional of a stochastic optimal control problem, right? So it has some running costs here, and it has some terminal costs, which is basically the negative log density, unnormalized. And the unique minimum is attained exactly by the score function. So I would say, I mean, as Molay said, it's highly related to optimal control. Actually, if you have the density, it's exactly a stochastic optimal control. So now I could give you a detour that you can also derive the setting where you have data samples but no density, but I will skip this now in the interest of time, and I want to discuss at the end of this theoretical part another divergence that we proposed a couple of years ago that we call log variance divergence. It's defined as this here. So it's basically the variance of this log density here, and it also, which is nice, it's with respect to a reference measure or reference drift here. So it's actually a family of divergences, right? So I can basically choose where I want to evaluate this divergence. And yeah, this has some nice properties. I mean, first of all, I can choose this reference drift more or less arbitrarily, which allows for exploration or exploitation, or to balance these two. I don't need to differentiate through the SDE solver, which is nice from a numerical perspective. And the kind of funny observation is that if I look at functional derivatives, so think of a Gateau derivative of this log variance divergence with respect to the forward drift evaluated at the reference drift being the forward drift, this is up to scaling exactly the derivative of the KL divergence, which surprised us a bit at the beginning. So now you might think, okay, if it's the same, so why should it be any better? Well, the catch is that if you look at Monte Carlo estimators, which I denote here with this little hat, we can see that the derivative is actually a control variate version of the KL derivative. And by control variate, I basically mean, for the ones who don't know it, I have an expectation, like a random variable where I add another random variable which has expectation 0, such that the expectations agree, but the statistical properties might improve. In particular, I might have lower variance. And this is really something we observe in numerics quite a lot. I mean, not always, but very often, that basically, yeah, this log variance loss fluctuates way less, which then also leads to faster and better convergence in the optimization, which is quite nice. And this basically, I mean, you just have to change 2 lines in your code to apply this. There are also some nice robustness properties, but yeah, in the interest of time, maybe just very quickly. So you have something that people call sticking the landing in the machine learning community. So basically at the optimum, you have variance 0 of your Monte Carlo estimator, which does not hold for the KL divergence. And you have something that we call robustness in high dimensions. So if you look at the relative error of some like product measure case, then this can be bounded uniformly in D. And this is also true for the KL divergence, but not true for any divergence, for instance, not for this chi-square divergence. So now at the end, I want to discuss an alternative loss. So now we go away from the BSDE loss and we enter the regime of pins. So physics-informed neural networks have also been discussed a couple of times already. I guess you all know them. What's nice here is that I can consider stochastic and deterministic evolutions. And I want to do this with this trick here. So basically, I parameterize I take this ansatz for my function v as follows here, and I basically automatically encode the boundary conditions, right? So there's the log target and the log prior here, and if I choose t accordingly, then I basically have automatically my boundary conditions in there. And what I learn is the z here, which I need in order to take care that it's really normalized. And I learn this phi, which is a neural network in the end, right? And then I can, simply brute force minimize the residual. So I think the pin idea is just take the PDE and minimize it, as simple as that. And I basically, randomly sample some points along which I evaluate my residual. And usually we take a uniform measure on like a compact set omega of the domain, which is already kind of a little bit dangerous because I kind of need to know where my density is actually supported. So I need to make a choice for this omega, which is an obvious disadvantage of this pin method. Still, we wanted to look at how this performs, and before I show you some numerical examples, I discuss quickly pros and cons of BSDE and pin-based method. So BSDE-based losses don't need second order nor time derivatives, which might be nice from a computational point of view. Then gradients of the solutions can be learned directly, which is not true for the pin losses. And an obvious drawback is that only stochastic dynamics can be considered. Whereas from the pin-based losses, I can consider also deterministic evolutions. It's by design basically simulation-free and no time discretization is needed. So I mean that I don't need to simulate trajectories at all. Off-policy training comes basically by design, which might be nice to kind of find modes of your target density. However, the obvious drawback is that I need to know somehow this essential support, so I need to know where my target is actually located. Particularly, I need to know my modes. And training of pins is known to be very sensitive to hyperparameter tuning, which also was a little bit annoying in our numerical experiments. But yeah, for the numerics, I basically now want to compare these different losses that I have shown you before. So just to recap, we have a stochastic evolution, we have a deterministic evolution, we have some BSDE versions, and we can either consider a general bridge, which has non-unique solutions, or a prescribed bridge, aka annealing strategy, score-based generative modeling, or Schrödinger bridge or optimal control. Okay, and I want to start with an easy example, a two-dimensional Gaussian mixture, but it's actually not so easy because it has 9 quite well separated modes. And yeah, so this, okay, so basically in this table, we show you a lot of numbers. So this first section here is basically more or less BSDE-based methods. So trajectory-based methods, either using the KL divergence or the log variance divergence. This here is approached with this pin loss for the SDE, so the stochastic dynamics, and this one is solved with the pin loss using the deterministic dynamics. And I don't want to read out all the numbers, but I mean, okay, maybe I should tell you what I'm measuring here. So the difference in the log normalizing constants and Wasserstein 2 distance, the effective sample size, a difference in the standard deviation of the marginals, which kind of measures mode collapse, and the gradient, the time for the gradient computation. And so what you can take from this numbers is that in this case, actually, I mean, many methods work quite well, but the general SDE and ODE losses work the best. And actually, in this case, the annealing strategy didn't work at all. And we tried to understand this, and actually we did understand it after some point, because these annealing strategies that people usually take in practice, in this case, it's just a geometric annealing, they're actually pretty bad. So this is actually the prescribed geometric annealing strategy that comes out in this example, and you realize that the modes are only recovered at the very end of the optimization, so it's very hard for a network to learn this drift that fulfills actually this dynamics. However, if we learn both the drift and the density simultaneously, this is what comes out. So this is like one realization of this non-unique solution problem. And you see that it nicely kind of transforms into the target density. You can also look at these realizations from marginals. I mean, just to show you some pictures. And here you see again that the annealing didn't work. This is what came out with the general loss. And here you can basically see the score-based generative modeling attempt. And you can see really here that it's somehow time inverting the Ornstein-Uhlenbeck process, right? And in the Schrödinger bridge attempt, the lines look more straight. Then we look at a double well example with highly separated modes, as you can see here. First in 5 dimensions. Look at the numbers. In this case, actually, the ODE method works best. And again, the method with the non-unique solutions works best. Also note that usually the log variance loss for the BSDE methods works much better than the KL loss. And we do this also in 50 dimensions, where again, the ODE method with the non-unique solutions outperforms the other methods. So to conclude, we have established optimal control, PDE, and path space perspectives on generative modeling, which now allows to carry over respective methods, which might also be nice to talk to you about, because now you can so if you're an optimal control person, you can simply take your favorite methods and apply them to sampling or generative modeling if you know the density, so that's important. We introduced sampling algorithms, which are already competitive to choose other sampling methods used in practice. The log variance divergence is a divergence we particularly like. Pins seem to be suitable for learning dynamical systems for training, for sampling. Kind of interestingly, often non-uniqueness actually helps to find a somehow better solution, which is a little bit frustrating from a mathematical perspective, but from an applied perspective, it paid off. So thanks a lot. Actually, the paper is online since today, so check it out, and thanks for listening.